So we are starting from U-Substitution method now. This is the very basic of integral calculus. Without substitution method, we can't move to the other concepts, that is integration by parts, integrating trigonometric function, trigonometric substitutions, like that. Okay, so first of all, let's have a look on U-Substitution method. Okay, but before that, I would like to suggest you two reference books. That means without the help of reference books or textbook, we will not get the insights of these contents. Okay, so I will suggest you Calculus, written by Ace Anton, and another one is for differential equation, written by Danish Zill. Okay, so for you I have the suggestion for these two books, that is Calculus, written by Anton Bivens and Davis, and for differential equation you can follow this one. So whatever contents I have written here, you will find these contents in Ace Anton's book, that means Howard Anton's book. So U-Substitution method, this concept you will find in section 5.3. Let me show you. Section 5, chapter 5, section 5.3 is dealing with integration by substitution, or we can say U-Substitution method. We can also think about it is Z-Substitution method, V-Substitution method. Variable doesn't matter, but the main thing is what is substitution method. So you will get this concept in section 5.3 from Howard Anton's book. Okay, that means then evaluating indefinite and definite integral part can be found in section 5.9, and also indefinite integral part can be found in 5.2 and 5.3. Is that okay? I'm just mentioning this book so that you can figure out whatever contents you have directly from your books. Okay, so then integration by parts can be found in section 7.2. Also the tabular method is there. Let me show you section 7.2, integration by parts, and you will see another method that is called tabular method. Okay, then integrating trigonometric functions, this part can be found in section 7.3. okay, we will find in section 7.3. then the trigonometric substitution concept, you will find this concept in section 7.4. integrating rational functions, it will be from section 7.5. integrating improper integrals, it will be from section 7.8. and integrating gamma, and for integrating gamma and beta function, there is, you will not find directly these two in Howard Anton's book, but you will find gamma function in another book, that is I have written another suggestion, another reference book for you, that is Differential Equation, written by Danish Chill. Okay, so in this book, Differential Equation, in appendices section, that means in appendix section, you will find gamma function. Okay, so but for beta function, we have to search in online so that we can get the insights of beta function, because there is no direct content you will find in these two books. So for beta function, we have to search in online, okay, or some other books. So let's start from U-Substitution method. So before starting U-Substitution method, you have to know some basic formulas. Okay, basic formulae. That means just like differentiation, you know that ddx of x power n is equal to nx power n minus 1, ddx of sine x, that is equal to cosine x. So like all these things, you have to know what is the integral for the common functions. Okay, so I am just writing some common formulas. That is, the first one is coming, integration of x to the power n dx is equal to x to the power n plus 1 over n plus 1. Remember, n can't be -1. This is the first common formula. Secondly, you can think about what is the integration of e to the power x. So it will be e to the power x. Again, e to the power -x dx. That means it will be negative e power -x. These are the common formulas. Or suppose integration of sine x with respect to x, that will be negative cosine x. You can see whatever result we are getting after integrating, that is called the antiderivative f of capital Fx, and these are the main functions. Okay, that means sine x is the original function and this is the antiderivative capital Fx, and sine x is the small fx. So you have to understand that always this relation holds. That means it is true for any function f of x, and if we integrate that function with respect to x, we will get the antiderivative. So dx of f of x is equal to actually the original function is small f x. So you have to know all these common formulas before starting U-Substitution method and the further concepts. So again, I am mentioning some other formulas. Integration of cosine x, that is equal to sine x. Or for this one, let's say integration of e to the power mx dx, it is actually e to the power mx over m. So remember, since we have the indefinite integrals here, so with all this for all these indefinite integrals, because since we have no lower and upper limit, so we can input a constant plus c plus c plus c. Is that okay? Integration of suppose we have a squared plus x squared dx, then we can write it is 1 over a tan inverse of x by a, integration of 1 over square root of a squared negative x squared dx, that is equal to sine inverse x over a. So whatever formulas I have written, you don't need to memorize all these formulas, because you can have a look for these formulas from this book. You will find all these formulas in any reference book. Suppose here you have all the formulas. Integration of sine u is equal to negative cosine u. So that means all the formulas are here. And since you are appearing all the exams from your home in this situation, so you can, before any problem, you can have a look on these formulas and you can figure out what you have to, which formulas you have to apply. Okay, so let's get back to our main concern. That is, we are going to discuss U-substitution method. So why we need U-substitution method? Or let's say it's substitution method only. You can take any variable. But since I am following this reference book, Calculus, written by Anton Bivens Davis, so that means the authors have used the variable u. So that's why that section, that means section 5.3, deals with u substitution method. Okay. So why do we need u substitution method? First of all, already I have mentioned that integration of sine x dx is equal to negative cosine x. That means for this function, you know what will be the antiderivative. But things will be critical if suppose we have integration of sine x plus 1 dx. So there is no direct formula for this part. So what you have to do? You have to convert, or you have to replace this one by a variable. That variable may be u, maybe v, maybe w. For the simplicity of this video, we are using u substitution method. Okay, so what we can do? We can consider, let us consider this inside part x plus 1, that means the part that we have here, as u. Why we are doing so? Because we know that sine x, integration of sine x is equal to negative cosine x. So that's why we are trying to convert this one to a variable u only. So integration of sine u will be obviously negative cosine u. So that's the thing we need to do here. So first of all, we have to follow the steps. Step 1. We need to consider a suitable function. Okay, as u. Consider a suitable function as u. You can also use v, w, whatever. So this part is important. I have mentioned here that function should be suitable function. That means whatever function we have considered here, that may be suitable, may not be. Okay, so why I am using this notation, this word suitable, you will understand later. But at first, let me show all the steps. So once we have considered a function as u, then the second step, in second step, we have to differentiate both sides with respect to the independent variable. Independent variable means, you can have a look here. In your main problem, you can see you have been asked to find the antiderivative, or you have been asked to solve this integral with respect to x. So x is our input or independent variable. Step 3. We have to keep x and dx terms in left side. I am mentioning left hand side, that is keep x and dx terms on left side and u or du or constant terms on the right side. Okay, so why we have done this one? Our target is to convert all x to a variable u so that we can directly apply the formulas, the basic formulas that we have. Okay, since the integral that we have here, that is not going with the direct formulas, that's why the method of U-substitution method is helpful. So after step 3, let's have a look on the next step, step 4. We have to replace x and dx in main function by u or du. That means our main task is to convert all x to u, and we have to integrate. That means we have to integrate for u. That means here we have integration for x, we have to integrate for u, or you can say du. Finally, step 5. Suppose you are successful in this part, you are getting the direct formula or the calculation is becoming easy, then in step 5 you will get the antiderivative. Antiderivative for u. So you must have to get back to x again. Okay, because you are starting a problem with x, but u is your consideration. So whatever part you will get finally, the result of that integration should be converted to, that means get back to x again, or get back to the input again. Okay, that means your antiderivative will be for u. You have to find the antiderivative for x. Okay, so we will follow all these steps, but remember, substitution method is one kind of trial and error process. Trial and error process. Okay, why I am saying it is trial and error process? Because whatever function we have considered, that should be suitable. That means suitable means finally after differentiation, if we are able to convert all x to u, or the calculations are becoming easy, or we are getting directly a formula. Okay, so that means whatever consideration we have made in step 1, that means that function will be the suitable function. And if we don't have the suitable function, we can think about other functions. So that means it is a trial and error process. You will learn by doing mistakes. Okay, so let's do by these steps. Let's try to solve this problem. So integration of, we have integration of sine x plus 1 dx. After this problem, we will take some problems from our reference book. Okay, so that we can have a lot of practice. So let's say we are taking x plus 1 as u. This is our first step. Step 1 says that consider a suitable function as u, but I have just taken a function from here. I am not sure is it a suitable or not. We will understand after finishing step 2 and step 3. So in step 2, you can see in step 2 we have to differentiate both sides with respect to the independent variable. So here we have the independent variable x. So let's differentiate in terms of x. So we are getting ddx of x plus 1 on left side and ddx of u. So here derivative of x with respect to x, it is 1. Derivative of 1, that means any constant, it will be 0. And here you are getting ddx of u is actually du dx. So finally we can write 1 equal to du dx. So step 2 is also completed. Step 3, keep x and dx terms, that means all x terms should be kept in left side and all u terms or constant terms should be kept on the right side. So I am doing this one. I am keeping dx terms in left side and du term on right side. So now integration of sine. We have considered x plus 1 as a variable u, and at the same time dx is converted to du. You can see dx is converted to du, and x plus 1, for x plus 1 we are using u. So now we can see that we have integration of sine u du, that is going with the basic, one of the basic formula, that is integration of sine x is equal to negative cosine x. So obviously integration of sine u will be negative cosine u. That means after replacing x plus 1 by u and dx by du, we are able to have the antiderivative, or we are getting the answer of this integration. That means this allows us that whatever function we have considered here, that is the suitable function. Okay, for this the calculations are becoming easy. That's why I have mentioned here in step 1 you have to consider a suitable function. If the function is not suitable, you will understand whenever you are going to replace x plus 1 or this function to u or dx to du, then you will understand if the calculations are going with the direct formulas or the calculations are becoming easy. Or okay, so you can say that that function should be, that function may be a suitable function, is a suitable function. Okay, so let's, already we have integrated for u, that means we have integrated for u and we have the answer, that is antiderivative or antiderivative. In step 5, what is mentioned here, get back to x again. So we have to get back to x, negative cosine. So instead of u, now we can write x plus 1 because we have considered this one. So this is our final result. So since we have no lower and upper limit, that means we have been provided provided an indefinite integral. That means that integral has no lower and upper limits. So definitely we can impose a constant c. So this is the result, and we can verify that relation. That means the relation we have established before, the relation is always true, that is ddx of antiderivative is equal to the original function. So have a look here, which function is small f and which function is capital F. At first figure out this is a small f function, that is a small f of x, and after this integral whatever we have found, that is capital F, or it is called the antiderivative. So we need to verify this one, because without this concept some of the parts of integral calculus will be missing. Okay, so that means you need to feel the fact. So let's differentiate the antiderivative function, and we want to verify whether the main function is coming back or not. Okay, so the function that we have here, Finally, negative cosine x plus 1 plus c. So I'm inputting here negative cosine x plus 1 plus c. So what we can do, using the concept of differential calculus, we can just separate these ones. Differentiation of negative cosine x plus 1 and differentiation of constant. So since we have negative 1, so negative 1 can be pulled out. So we have differentiation of cosine x plus 1. Differentiation of constant is always 0. So here negative. Now differentiation of cosine x plus 1. At first try to understand that if we have this can be solved by using chain rule. So what is chain rule? I am discussing directly here. You know that cosine, differentiation of cosine x is equal to negative sine x. You will find all these formulas in your textbook. Okay, the formulas are here. Differentiation of cosine x is equal to negative sine x. So now we have some other part. So for this, how we can find the derivative? Just at first consider this x plus 1 is a simple x. So it will be differentiation of cosine x is negative sine x. So differentiation of cosine x plus 1 will be negative sine x plus 1. And remember, you have considered x plus 1 as x, so it should be again under differentiation, and these two parts are multiplied. Okay, this is called chain rule. So if you need to find the antiderivative, so at that time the concept of differential calculus are also helpful. Okay, so negative negative, here you can see negative, here you can see negative, so negative negative, you will get positive. Now positive sine x plus 1. Now differentiation of x is 1 and differentiation of 1 is 0. So that means finally you are getting from here on. Or we can say it is just sine x plus 1. Now let's verify sine x plus 1. We have started with this. So f of sine x plus 1 is actually f of small f of x. So that means we are able to prove that it is equal to small f x. So we are differentiating the antiderivative. That means the answer of this integral. Okay, the answer of this integral is this one. If we differentiate this part, we will get main function. So you don't need to verify this one, but for this, since I am starting from the very beginning, so that's why I have discussed this one again. Okay, always this concept will be true for any integral part, any indefinite or definite integral. You can check this relation, and it must be that differentiation of antiderivative will be the main function. Okay, you can see we are differentiating antiderivative and we are getting the main function back. That's why differentiation and differentiation and integrations are linked up. Okay, these are the opposite criteria. So okay, we are discussing U-substitution method. I hope already you have understood why we are using U-substitution method, because things will be critical if we have a complicated function and it is not going with directly the formulas. So let's take some examples from our reference book. You will find U-substitution method in section 5.3. In section 5.3 from Anton's book. Okay, so let me take one problem from 5.3. I'm going to the exercise part so that you can have the basic idea from this exercise part. Okay, so let's take any random problem. Let's take 31. So in 31, you can see we have integration of e to the power sine x cosine x. That means we have to integrate this function. This is our original function, and we need to find the antiderivative for this function. Okay, so let's write this one. The function is e to the power sine x cosine x, and we are integrating in terms of x. Okay, so if you have a search on your textbook, then you will not directly find any formula for this type of functions. Okay, so this is one complicated example or problem. So what we have to do here, we can think about substitution method. Okay, which suitable function can be taken as u so that we can easily integrate this one, so that we can easily find out the antiderivative. So that means you have to figure out. Okay, so again, have a look on the steps of U-substitution method. Step 1, consider a suitable function as u. Then we have in step 2, we have to differentiate both sides with respect to the independent variable x. Okay, and then we need to keep the x terms and dx terms in left side and u and du term on the right side. Finally, in step 4, we will try to solve the integral, and then after finding the antiderivative that will be for u, we have to get back to x. So this is called U-substitution method, but your function should be the suitable function. Suitable means for the function, for that, if we have finally one easy problem, or if we are able to convert that indefinite integral to our easy notation or form, then we can say that that function is suitable function. Okay, so you have to remember that U-substitution method is a trial and error process. So let's take the help of U-substitution method here. So at first, I have mentioned that you will learn by doing mistakes. Okay, so if we take suppose we are taking cosine x as u. So step 1 is completed. We have considered a function as u. Then in second step, we have to differentiate with respect to this variable x. So I am not sure whether this function, that is cosine x, is suitable or not. We will understand within some seconds. So differentiation of cosine x is equal to negative sine x, and differentiation of u with respect to x, you are getting du dx. So negative sine x dx is equal to du. So that means we have done step 1, step 2 is also done, and we have come up to step 3. That means we are keeping the x terms and dx terms in left side, and on right side we are keeping the u terms. Okay, so you can see that here we have negative sine x dx. Okay, so we have e to the power sine x, and cosine x is converted to u, but for dx, what we can write, dx equal to du over negative sine x. So things are going to be very complicated. Okay, because still we have x here. So whatever function we have considered as u, that is not suitable. So we have to think again. That is called the trial and error process. So okay, you will learn by doing mistakes. So instead of instead of taking sine x as u, sorry, instead of taking cosine x as u, now we are taking this one, sine x as u. Now the second step is to differentiate the function with respect to the main variable or input variable. So differentiation of sine x, you are getting cosine x, and differentiation of u with respect to x is equal to du dx. Okay, so what you are getting? You are getting cosine x. That means our target is to keep x terms and dx terms in left side, and on right side u terms or du terms, okay, on right side. So here, now we can easily see that after considering sine x as u, what we are getting? E to the power, instead of sine x, now we can write e to the power u, because sine x is u. Now automatically cosine x dx has been found here. So for this we can write du. So this is becoming very easy this time. So that means instead of cosine x dx, what we can write? We can write du. Okay, and now we can think about the formulas. Integration of e to the power x dx is equal to e to the power x. We know this basic formula, and it is going with this one. Integration of e to the power u du, that is nothing but e to the power u. We have found the antiderivative. So now we are understanding that, whatever function we have considered here as u, that is correct, that is the suitable function. Okay, so remember, whenever you are applying U-substitution method, your function should be the suitable one. Okay, otherwise calculations will be difficult. So now integration of e to the power u with respect to u will give us the antiderivative e to the power u. Since we have started with indefinite integral, there is no lower and upper limit, so we can impose a constant c. Now last step of U-substitution method is, we have started with x term. Our given problem is for x term, so we have to get back to x. So whatever part we have here u, that should be converted to x, sine x. So we can write e to the power, instead of u we can write e to the power sine x, e to the power u, e to the power sine x plus c. Okay, so this is our final answer, or we can say this is the antiderivative. Antiderivative means capital F x. We can also verify, if we differentiate this part, we will get the main function back. Okay, that is the relation between differentiation and integration. Okay, so what is integration or anti-differentiation? The process of finding antiderivative is called the anti-differentiation or integration. Do you understand? I hope you understood. Okay, so let's take another example from exercise. Let's take any random function here. Let's take 34. Here we can see that integration of e to the power x plus e to the power minus x over e to the power x negative e to the power minus x. So let me write this function here. We have an indefinite integral e to the power x plus e to the power minus x over e to the power x negative e to the power negative x dx. Let me check again. Yeah, I have written the correct thing. Okay, so you can see that whatever function we have now This is called the integrand. It is the integral sign. We are integrating with respect to x. Okay, so whatever function we have here, that is a complicated function. Okay, there is no direct formula for this one. You can see we have e to the power x, e to the power negative x. At first we can think about integration of e to the power x, that is the result is e to the power x. Integration of e to the power negative x dx, that is equal to negative e to the power negative x. So at first we can think about all these formulas, but these are the common functions. But here, whatever function we have here, that is not the common one. So what we can do, we can take the help of U-substitution method. Okay, so here we have, I am writing again, e to the power x plus e to the power negative x, e to the power x, negative e to the power negative x dx. So since we don't have any direct formula for this one, we can apply U-substitution technique. And remember, U-substitution technique or substitution technique is one kind of trial and error process. Okay, you can consider any function as u, maybe that will be wrong. Okay, so you have to look for the correct function. So first of all, if I take the upper part, what will be the problem? Let's verify. So if we take e to the power x plus e to the power negative x as u, I am not sure is it suitable or not. Okay, we will understand within some seconds. That is ddx of e to the power x plus ddx plus e to the power minus x is equal to ddx of u. So we are getting differentiation of e to the power x is e to the power x, differentiation of e to the power negative x is equal to e to the power negative e to the power negative x. Okay, that is equal to du dx. So in next step, what we have to do, we have to keep x terms, that is e to the power x negative e to the power negative x dx in left side, and on right side we need to keep u terms. So that are the steps. Step 1 is to take a function as u. In step 2 we have to differentiate with respect to the independent variable, and then in step 3 we have to keep the x terms in left side and u terms on right side. So now you can see that whatever function we have taken the upper function as u, but here finally we have found e to the power x negative e to the power negative x dx. So we have found the multiplication part or product part, but here we have the same function e to the power x negative e to the power x. You can see here we have negative functions are same, but we didn't get this type of figure here. The actual part will be just like this one. From here we can say this one, but whatever we have finally after differentiation, that is not going with this one, so it's getting complicated. So that means the function that we have as u here, we have considered as u, that is wrong, so it is not suitable. So that's why whatever we have considered, that is wrong. So I am discussing by this way so that you can learn by mistakes. Okay, so instead of the upper part, now I am targeting for the lower part. So let's take the lower part as u. I'm still not sure what will be the result finally. Is it suitable or not? Okay, it is again a question. So now I have taken the lower part. So let's differentiate again. Once we have considered in terms of once we have considered a function as u, the second step is to differentiate. So we are differentiating both sides. So differentiation of e to the power x is becoming e to the power x. There is a negative, and differentiation of e to the power negative x will be negative e to the power negative x. So see, every time before solving an indefinite or definite integral, we must have to know what is a differential calculus. We must have to recall all the formulas from differential calculus. Okay, so we can't avoid all these things. So du dx. Now what we are getting? We are getting e to the power x plus e to the power negative x dx. Okay, negative negative positive, and you are getting du dx. Okay, so in next step we have to keep the x terms and dx terms in left side, and on right side we can keep the u terms or constant terms. So here e to the power x plus e to the power negative x dx is equal to just du. On right side we can keep u terms or du terms, or with du terms we can keep any constant. Okay, if we have finally a constant, then so okay, finally we have found now e to the power x plus e to the power negative x dx as du. So now see, you can see that if I write again in another way, the same function can be written or expressed as e to the power x negative e to the power negative x, and the upper part is e to the power x plus e to the power negative x dx. We can write by this way. So you can see this part is automatically here. So that means instead of this one we can just write du. So whatever we have considered, whatever function we have considered as u, that is the correct or suitable one. Okay, that is what is called U-substitution method. So let's try to solve this one. Now at first replace the lower part is u, we have considered it is u, and this one is becoming du. So now you know that integration, there is a common formula, integration of 1 over x dx, that is equal to natural log, that is ln or ln mod x. You often do a mistake, you just write this one. You do a mistake that you have a practice of writing by this way, integration of 1 over x dx is equal to ln x, but that is wrong. We have to use the natural log of modulus x, ln modulus x. Okay, that is the correct formula. You will find all these formulas in your reference book. This one, integration of 1 over u du is equal to ln modulus u. Okay, so let's try to solve this one. Integration of 1 over u du, that is going with this formula, so we are now easily writing this one as natural log of modulus u, that is ln modulus u. Okay, this is our antiderivative, but don't forget that still we have one task left, that is we need to get back to x again. So we have considered e to the power x negative e to the power minus x as u. So let's input this one, e to the power x negative e to the power negative x plus c. Since we have indefinite integral, so in final result we can input a constant plus c. So this is called the U-substitution method. So whenever I have given the overview, you can see whatever contents we have in week 1, week 2, and week 3 that are here. So we have already finished this one. U-Substitution method. Now you can practice. Okay, so by the help of U-Substitution method, we have taken two problems from indefinite integral from exercise. Okay, and we have found the result. Let's take one example from definite integrals, and you will find definite integral concept in section 5.9. Okay, so again, let's take one example from section 5.9. This time that problem should be for definite integrals. 5.9, evaluating definite integrals by substitution method. Okay, so again, substitution method will be helpful. So let's take one random problem from here. Let's take this one. That is, in upper part we have x plus 2, and in denominator we have a square root of x squared plus 4x plus 7, and we are integrating from 1 to 3. That is, this is a definite integral this time. So let's take this example. Integration of, what we have here, we have x plus 2, x plus 2 over square root of x squared plus 4x plus 7. We are integrating in terms of x, and the limit that we have here, integration from 1 to 3. Integration from 1 to 3. Okay, so this is the definite integral. So at first, have a look on this function. There is no direct formula. You will not find a direct formula for this integral, okay, for this function. So what you have to do, at first you can think about U-Substitution method. So let's take that concept into account. So what we can consider, we can, if we consider the lower part, that means the part that is inside the radical sign in denominator. So I am taking that one here. Let's see whether it is suitable or not. So x squared plus 4x plus 7 equal to u. Okay, I need to mention here that whenever you are evaluating definite integral, you will finally get one real number. That means the result will be a real number, or we can say that will be a finite value. Already we have discussed whenever we have started this video. Or this will be the area under this function from x equal to 1 to x equal to 3. So x equal to 1 is the lower limit and x equal to 3 is the upper limit. So before solving this integral, try to have all these concepts in mind. So what we can do here, we have considered x squared plus 4x plus 7 as u, but for this definite integral, at first forget about the limits. Suppose we don't have the limit. At first try to find the antiderivative for the corresponding indefinite integral. That is, here we have the indefinite integral, integration of x plus 2 is square root of x squared plus 4x plus 2 dx. Okay, at first we need to solve this one. So we have already taken x squared plus 4x plus 7 as u. Then the second step will be differentiation, because U-Substitution method allows us to differentiate that function. Okay, so if we differentiate that function, x squared plus 4x plus 7, differentiation of u, so what we are getting, differentiation of x squared is becoming 2x, differentiation of 4x is 4, and on right side differentiation of u in terms of x is equal to du dx. So from this part you can see we can take 2, we can factor out 2, that means 2 times x plus 2 is equal to 2x plus 4, so is equal to du dx. So what we have, the final is step 3. Step 3 says that we need to keep the x terms and dx terms in left side, and on right side du and constant terms. So here we have constant 2, on right side it will be 1 by 2. So if we can have a look on the steps again. We are following these steps. Step 1 is to consider a function, then we have to differentiate both sides, then after differentiation keep x and dx terms in left hand side, and on right side u terms, du terms, and constant terms. So finally you have to integrate for u. Then you will understand that if the integral is becoming easy, you can apply the direct formulas. Then you can say the function that you have considered previously, that is a suitable function, and you will get finally the antiderivative for u. So finally we have to get back for x. So we are following these steps. Okay, so you can see that for this integral we can write by this way: integration of 1 over square root of x squared plus 4x plus 2 times x plus 2 dx. We are just rearranging the previous function in this way. Now we can see that here we have x plus 2 dx, automatically here we have x plus 2 dx. So whatever function we have considered here, that is a suitable function. Okay, that means for this the calculation is becoming easy. You will understand here. So integration of 1 over a square root of, we have already considered this part as u. Okay, so I am writing u here. That means we have considered x squared plus 4x plus 7 as u, and this part is becoming x plus 2 dx is du over 2. So it is du over 2. Now let's try to solve this integral. Okay, so first of all, using the property that you have 1 over 2 as constant, so we can pull out this constant before. So we have 1 over root over u du. Then we can write 1 over 2 integration of 1 over u power 1 by 2 du. Or we can write 1 by 2 integration of the reciprocal of this part will be u power negative 1 by 2 du. Now it is going with a direct formula, that is, you know that integration of x to the power n dx, that is equal to x to the power n plus 1 over n plus 1. So we can apply this formula because here we have u to the power n, so u to the power n plus 1 over n plus 1. So let's apply this formula here. One by 2 u to the power negative 1 by 2 plus 1 negative 1 by 2 plus 1. Okay, so we have finally solved this integral. So here 1 by 2, we can write it will be negative 1 by 2 plus 1. Okay, so here we have u to the power 1 by 2. That means 1 negative 1 by 2 is actually 1 by 2. Again we have 1 by 2. So you can see that if we simplify this part, 1 by 2 and this part will be cancelled. So here finally we are getting u power 1 by 2. That means root over u. So whatever result we have found, that is our antiderivative. But don't forget to get back to the x function. So here you have x term, that is x squared plus 4x plus 7. So x squared plus 4x plus 7, that is your final result. So we had actually the definite integral, not indefinite integral. We have the definite integral from 1 to 3. But whatever we have done here, we have solved at first the indefinite integral part. For this, the result is becoming root over x squared plus 4x plus 7. That is actually the antiderivative f of capital F of x. So in upper part, we have x plus 2 and in lower part x squared plus 4x plus 7. Now think about the limits. We had 1 to 3. So we are integrating at first from 1 to 3. So you must know that we have the fundamental theorem of calculus. Integration from x equal to a to x equal to b, f of x dx, that is equal to, at first you have to find the antiderivative with upper limit and lower limit. So antiderivative at upper limit, negative antiderivative at lower limit. This is called the fundamental theorem of calculus. So before applying fundamental theorem of calculus, what we have done, we have solved the indefinite integral and we have found the antiderivative. That means this is f of x. Okay, so with upper limit 3, lower limit 1. So what we can do now, from this part we can apply upper limit where we have x terms, again negative, lower limit 1 where we have x term. Let me write again. So we are getting a square root of 3 squared. Here we have x squared, so 3 squared, upper limit 3. So 3 squared plus 4 times 3 plus 7. And there is a negative square root of, again in this place we can input 1. So 1 squared plus 4 times 1 plus 7. So what we are getting finally? Square root of 9 plus 12 plus 7, negative square root of 1 plus 4 plus 7. So actually we have finally 9 plus 12 plus 7 will give you root over 28, negative 5 plus 7, that is 12. If we simplify this one, then root over 28 negative root over 12 is equal to 1.827. I am using my calculator. Okay, so this is the result. That means finally we have a real number. Since we have the definite integral having lower limit and upper limit, so finally we have found a real number or finite value that is defining the area under this function from x equal to 1 to x equal to 3. So this is how we can apply U-substitution method for finding the antiderivative or area. Okay. So we will take another example from our exercise, then we can conclude U-substitution method here. So you have to remember that U-substitution method, for U-substitution method, you must have to remember or recall all the formulas that you have for integral calculus. But for this semester, since you were studying from your home, so you can directly have a look. You don't need to memorize all these formulas. You just need to recall. You just need to have a look on the formulas. Okay, so let's take another problem from our reference book. Let's say this one, number 40. We have integral from pi squared to 4 pi squared, and the function is 1 over root over x sine root over x dx. Let me write this one at first. So here we have the function 1 over root x sine root x dx. Integration from pi squared to 4 pi squared. So this is a definite integral, okay, because we have lower limit and upper limit involved. So at first, what we can do, it is a definite integral, okay. So we can at first find the antiderivative for the respective indefinite integral. So the indefinite integral here we have 1 over root x root over sine root over x dx. We can at first solve for this one, okay. Then after having the antiderivative, we can apply upper limit 4 pi square and lower limit, that is we can apply the fundamental theorem of calculus, f of b negative f of a. So this is how we can solve the definite integrals. So for definite integrals, we at first have to consider the respective indefinite integral, okay. The method that I am doing here, that means if we have a definite integral, we are skipping these limits at first, and we are trying to find the antiderivative or answer of this integration for the respective indefinite integral. After having the antiderivative, we can apply upper limit and lower limit. But in your reference book, you will see another technique. That means there are two methods for evaluating definite integrals: solution by method 1, solution by method 2. I am using this concept, method 1, okay. That means method 1 says that at first we have to find the respective indefinite integral and then finally input upper limit and lower limit. So this process will be easier for you, because whenever we will start the complicated problems, we will start to solve our complicated problems like this one, that is integration of trigonometric function, integration of trigonometric substitution, integrating rational functions, improper integrals, gamma function, beta function. So at that time, method 1 is helpful. So that means it should be a practice, okay, with method 1. Method 2 is also helpful, but I will suggest you try to follow method 1. That will help you in upcoming contents. Okay, so let's try to find this integral at first. Again, we don't have a direct formula for this one. So what we can do, we can take the help of U-Substitution method. So let's take any function that may be suitable, may not be suitable. Okay, so that's why it is called U-Substitution method, or substitution method is called the trial and error process. So if we take root x, this time I am directly taking root x because okay, it will not be suitable. If we take this one, yeah, so root x as u. So whatever function you will consider, that should be suitable. Okay, so you will try to figure out, okay, which function will be suitable one, and this is based on practice. If you have a lot of practice, you will easily figure out that this function should be u, or otherwise you have to use the trial and error process. But things will be easier, you can save your time if you have a lot of practice over U-Substitution method. So definitely for this integral we can take root x as u. So here we have already considered root x as u. Now if we differentiate root x, that means we are differentiating both sides. So differentiation of root x is equal to 1 over 2 root x. Okay, it is going with the formula. Let me describe: ddx of x power 1 by 2. That means ddx of root x is equal to ddx of x power 1 by 2. And if we apply this one, x power n x power n negative 1, so that means 1 by 2 x power negative 1 by 2. So we are getting 1 by 2, 1 by x power 1 by 2, and finally 1 by 2, 1 by root x, so 1 by 2 root x. So that means derivative of root x is actually 1 by 2 root x. So that's why I have directly written derivative of root x is equal to 1 by 2 root x. And now on right side we have du dx. So I have already mentioned that finally after differentiation you have to keep the x terms and dx terms in left side. On right side try to keep du term and constant term. Now see, this part and this part are equal. I have just written in different ways. I have just kept the x terms in left side and u terms and constant term on right side. 1 by 2 is here, on right side it will be just 2. So what is the advantage of taking root x as u? Let's see. Integration of, we can rearrange the function as, we can rearrange the previous function as this way: root x sine root x times 1 over root x dx. So integration of sine root x is actually, we have considered u, and for this part automatically we have 2 du here. So that means the function that we have considered, that is a suitable function, root x. So now it is easy to solve this integral, that is 2 is constant, we can pull out 2 before. So integration of sine u du, and now it is going with the direct formula. You know that integration of sine x dx, that is equal to negative cosine x. So for here we have u, so it will be 2 negative cosine u. Is that okay? That is the answer. So don't forget to get back to x. So here we have negative 2 cosine u. So finally we can write negative 2 cosine root x. Instead of u, we can write cosine root x. That means we are transferring u to root x. So this is our final antiderivative. For the integral 1 by root x sine root x dx. Now, you have in your question, you have the lower limit and upper limit. Lower limit is pi square, upper limit is 4 pi square. So this will finally give us a finite value, that is area. Okay, so let's try to think about this lower limit pi squared and 4 pi squared. So at first what we have done, we have found the antiderivative for this indefinite integral. So now let's impose lower limit pi squared, upper limit 4 pi squared for this function root x sine root x dx equal to, this is our antiderivative. So with this antiderivative, we have upper limit 4 pi square and lower limit pi are 4 pi square and lower limit is pi squared. So let me check again, pi squared and 4 pi squared. Yeah, that means we are applying the fundamental theorem of calculus. Fundamental theorem of calculus says that integration from a to b f of x dx, that is equal to antiderivative at upper limit negative antiderivative at lower limit. So we are going with this one. We have the antiderivative here, so we can input upper limit where we have x, because we have the antiderivative f of x with b and a. So this is our input. In that part we are inputting b and a. So at first try to figure out the input here. Here we have input x. In that place we need to input the upper limit and lower limit. So first of all, antiderivative at upper limit. Okay, at first, since we can see that negative 2 is constant, why not we can bring this one? So let's bring this negative 2 before this antiderivative or this square bracket. That will help us to calculate easily. Okay, upper limit 4 pi squared, lower limit pi squared. So this is our input x. So at first let's input fundamental theorem. Let's apply fundamental theorem. Fundamental theorem says that antiderivative at upper limit negative antiderivative at lower limit. So our upper limit is 4 pi squared, lower limit is pi squared. We are plugging upper limit and lower limit where we have x. So finally what we can do, negative 2 cosine root over 4 pi squared will give you 2 pi negative cosine root over pi squared will be pi. So cosine 2 pi, that means cosine 360 degree, cosine 2 pi, that is cosine 360 degree is actually positive 1, and cosine 180 degree is actually negative 1. Okay, so we have found these two values. So finally we can solve, that is negative 2 1 plus 1, negative, negative, positive. So we are getting actually negative 4. So this is the result for our given definite integral, that is pi squared 4 pi squared 1 over root x sine root x dx. So negative pi is the answer. Negative 4 is the answer. Okay. So finally, whatever we have found, that is actually the area. Since it is the finite value, it is the area. Okay.